Okay, Bismillah ar-Rahman ar-Rahim. Today we are going to start about linear programming, model formulation and graphical solution. So we will learn about linear programming. First of all, is not a programming in that sense that it's kind of a language like C++ or Fortran or other languages. It is a mathematical programming technique. And we will be learning in this chapter graphical technique, how to solve a mathematical formulation of linear programming, which is an optimization technique graphically, and how to model the problems. Linear programming has many applications, not only in management. It has application in all different areas, engineering, medicine. Wherever the optimization is required, we can use linear programming. So let's see what we are going to learn in this. We will learn about, in this topic, our model formulation, maximization model. First we will see a maximization problem, and we will see its graphical solution of linear programming models. And then we will see another example of minimization. And then in the later chapter, we will see irregular types of linear programming models, some special cases, and characteristics of linear programming problems. What are the characteristics of LP problems? Sometimes we, instead of saying linear programming, in short, we call it LP, linear programming. All right? So many management decisions involve trying to make the best use of limited resources. And when we say resources, what does it mean? Resources mean machinery, labor, money, time, warehouse space, raw material, anything is resource. Okay? Money, time, machinery, labor hours, warehouse space, raw materials. All these things are called resources, and we want to make efficient uses of resources. Remember that we talked about what is management. Management is a process of getting things done effectively and efficiently. So we want to use our resources efficiently. Linear programming is widely used mathematical modeling technique, which is designed to help managers in planning and decision making relative to the resource allocation or resource optimization. It's belong to the broader field of mathematical programming. There are many other different mathematical optimization techniques, and linear programming is one of them. So in this sense, programming refers to modeling and solving a problem mathematically. It is not a computer programming. It is a mathematical optimization technique. Some examples of successful use of linear programming. For example, development of a production schedule that will satisfy future demands for a firm's production and at the same time minimizing total production and inventory costs. Many problems have product mix problems. So we will see, in fact, the product mix problems in the first examples, where you have a choice of either use this much or that much product to minimize the total cost or total profit. So this is one of the main application. Selection of the product mix in effect to make best use of machine hours, labor hours, while maximizing the firm's products, or rather maximizing the firm's profit rather than products here. It's a mistake here. Determination of grades of petroleum products to yield the maximum profit. There are grades of petroleum like, high-speed diesel, petrol, different grades are there of petroleum, and how much each to produce to maximize the profit, or again minimize the cost. selection of different blends of raw materials to feed mills to produce finished feed combination at minimum cost. We may have blending the cloths, cotton, polyester, wool, etc. How much to mix it to minimize the cost, etc. Determination of a distribution system that will minimize total shipping costs from several warehouses to various market locations. In transportation problems, we need to minimize the total distance, or there are assignment problems also. We need to minimize the time taken by machines, for example, when we are allocating or assigning the machines, or allocating labors, or maximizing the efficiency of people. So these are the different kinds of applications of linear programming. One of the earliest use of linear programming was in hospitals. It was a diet problem. So you want to give the best nutrition to the patients and minimize the diet cost. So this was the first earliest example in the civil side. An overview of linear programming: we will have an objective function. Objective of business decisions frequently involve maximizing profit or minimizing costs. Linear programming uses linear algebraic relationships to represent firm's decision given a business objective and resource constraints. So our objective function, which will be either to maximize or to minimize, will have linear relationships there. Also in our constraints, there will be linear algebraic relationships. Steps in applications: we identify problem as solvable by linear programming because there are, we have to fulfill the requirements of linear programming, that linear programming has certain assumptions and we cannot use it for every kind of problem. Okay, the mathematical relation should be linear. So first of all, we have to identify that it is solvable by linear programming. Then formulate a mathematical model of the unstructured problem, solve the model, and of course implement it. The components of model will be, there will be decision variables, which are mathematical symbols representing levels of activity by the firm. Decision variables are, we are going to decide about how much, for example, number of products we have to produce to minimize the cost or maximize the profit. This is decision variable. The decision variable could be how to minimize the total transportation cost, etc. Maximize the efficiency of people in such a way that we allocate or assign the people according to their efficiency. So these decision variables are these things which we have to decide. Objective function is a mathematical relationship, linear relationship, describing an objective of the firm. In terms of decision variable, this function is to be maximized or minimized. Okay, so we will have one objective function which will be either to maximize or to minimize. And of course there will be constraints. We cannot maximize the profit to infinity, right? Or minimize the cost to zero. There will be constraints. So these constraints, requirements, or restrictions placed on the firm by the operating environment is stated in a linear relationship of the decision variables. The constraints and the objective functions will be linear. That's why it's called linear programming. And then there will be parameters. These are numerical coefficients and constant used in the objective function and constraint. For example, a company is making, we will see an example, a company is making a furniture, company is making tables and chairs. And the decision variable will be how many number of tables to make and how many number of chairs to make to maximize the profit. Now the profit, the table may be bringing is 7 reals and the chair may be bringing 5 reals per unit. So this 7 or 5 are kind of a constant this in the objective function, and that is called parameters. Similarly, in the constraints, there will be some constant numbers or coefficients which will be called parameters. Like 4 hours of carpentry are used to make one table. This 4 is a technological coefficient in the constraint, right? Or on the right hand side, how many number of available hours are available to us in a resource. How much the resource is available, that is a parameter. So we will have parameters, we will have decision variables, we will have an objective function, and of course we will have constraints. The summary of model formulation steps: define the decision variables, we read the problem, and we identify what we have to decide, what we are going to decide about. So decision variables we have to find out and define them. And then define the objective function, write down the objective function in terms of these decision variables, and then write down the constraints. Now, one of the most common LP application is the product mix problem. 2 or more products are produced using limited resources such as personnel, machines, and raw materials. We will see this problem, product mix problem. The profit that the firm seeks to maximize is based on the profit contribution per unit of each product, and the company would like to determine how many units of each product it should produce so as to maximize overall profit given its limited resources. We will see one example now. This is an example here. We have 2 products. The company is making 2 products, bowls and mugs, and they are using 2 resources. One is material resource is used, which is clay, and another resource is the labor hours. And of course we have the profit which is for bowl, it is $40 per unit per bowl, and $50 per mug is the profit. Very expensive kind of mug and and bowls are there. We have, this is a product mix problem. We said that we will see the product mix problem. It is the most of the time this is used for, linear programming is used for that purpose. Okay, how many bowls and mugs should be produced to maximize the profit given labor and material constraints? Labor and material constraints are there. The right hand side, how much the labor hours available to us and how much clay is available to us. I'm afraid it is written very small here. The clay is 120 pounds per day. All right, 120 pounds per day is the total clay available in a day, and the total labor is 40 hours per day. So if 8 hours is the work, one laborer works for 8 hours, then it means that 5 laborers may be there working in that company. This is 40 hours per day is available the labor. So this is the product resource requirement, and unit profit is the objective is to maximize the profit. So what we can do is we can, what do you think? What are our decision variables in this one? Yeah, so the decision variables are how many number of bowls to be made and how many number of mugs to produce to maximize the profit. These are our decision variables. So first of all, we identify the decision variables and we define them. So the step will be to define the decision variables. We say, and usually I like to define by x with subscripts x1 and x2. We can define by x and y and z, etc. I prefer by subscripts. X1, let's say, is number of balls to produce, and x2 is number of mugs to produce. Now from here, in this example, what do you think? What is our objective? Objective is to maximize the profit. The profit is given, so we want to maximize the profit. So we write down the objective function, maximize. Okay, let's say z is the profit, is equal to 40x1. 40 is the profit of one bowl. $40 is profit of one bowl, and 50 is for one bowl. And we have defined x1 as number of bowls and x2 as number of mugs. So we write down 40x1 plus 50x2 is our objective function. Okay? And the constraints are very clear also. There are only two constraints. Okay? What are those? Labor and play, right? So let's write down first of all labor constraint. Okay, we have x1, 1x1, let's say 1, sometimes we don't write 1, it's understood. 1x1 plus 2x2, okay, and we have, as you may be not able to see it, we have 40 hours per day available to us, okay, and these are also hours used for making one unit. So 1x1 plus 2x2, one way is to write down A equal to 40, because 40 hours are available. But we may not be able to use 40 altogether. Alright? It's possible that we may use only 36, 38, etc. The maximum is 40. So we will write down the constraint in less than or equal to constraint. And similarly, we can write down the constraints for clay. We have 4 pounds of clay needed for bowl. 4x1, x1 is the number of bowl you make, plus 3x2, and again on the right hand side we have 120 pounds of clay is available to us, 120 here, and not all perhaps would be used, so less or equal to. These are the two constraints. One more constraint we put, and that is called non-negativity constraint. The non-negativity constraint is that the decision variables cannot take negative values. Okay, they can take 0 or positive value, but not negative value. We call it non-negativity constraint. x1 and x2 both should be greater or equal to 0. Okay, this is a mathematical formulation of this problem. It's very easy, and of course, now we have seen a simple example which we can solve by graph. That's why it is called graphical technique, which we are learning. But if we have more than 2 decision variables available, okay, if we have more than 2 decision variables, then graphical technique will not be able to work. So in this chapter, the problems we are going to see, in this chapter, the problems we are going to see are only with 2 decision variables. Let me solve this problem and then we will go through these slides quickly. Okay, now the graphical technique is that we graph this. We graph it and axes we choose the decision variables. X1, number of mouse, and X2, number of marks. Now to plot this, you can see over here, if you make it equality, it becomes a straight line equation. Right? And the straight line equation we can easily draw. We need only 2 points to make a straight line. And it's easy to make 2 points on the coordinates. If we have 2 points on the coordinate, we just join them together, that becomes straight line. So this will become x1 plus 2x2 is equal to 40. Alright? x1 plus 2x2 is equal to 40. Which means that if x2 is equal to 0, x1 will be equal to 40. And if x1 is equal to 0, x2 will be equal to 20. We need only 2 points to make a straight line. Let's say this is x1 is 40 here. Alright? And let's say this is 20 here. These 2 points we just join. This is 40, 0. This is 0, 20. 2 points, right? This is 40, 0. This is 0, 20. These are the 2 points. We have joined them. Now since it is less than or equal to, this constraint is valid on this side or this side? Down. So for example, if we have x1 is equal to 40 and x2 is equal to 20 here, it will be more than 40. If x1 is equal to 40 and x2 is equal to 20, it is above right hand side, which is 40, which means that it is invalidating the constraint. It is not what we call it, it's not it's not respecting, okay, it's not respecting the constraint. So the constraint is valid on this side, right? And we draw the next one, 4x1 plus 3x2. 4x1 plus 3x2, make it equality again, equal to 120. Then if x2 is equal to 0, x1 will be equal to 30. And when x1 equals to 0, x2 will be equal to 4. So we have, let's say this is 20 here, then this may be around 30 here. Okay, and this is about, this is 40. Okay, double of that. And we just join. Okay. Again, the constraint is valid on this side. Now, any point here, for example, or here, it is respecting one constraint, but it is violating the other constraint. So when both are satisfied, then that is called the feasible region, which means that the feasible region in which the solution lies, and that is feasible region is this area. This is the feasible region. Okay. Now there are two methods to solve this problem. One is called corner point method, and another is called the iso-profit line method. In graphical technique, iso-profit line method, there are two methods to solve. One is corner points and another is iso-profit. The corner point we will discuss first. There are three vertices of this region or corners, or rather four. Okay, and we can work out the profit at each point, and the maximum gives the our optimal answer. So this point is 0, 0. This point is 30, 0. And this point is 0, 20. Now for this point, intersection between the two equations. So what we can do is we can just multiply this equation with 4, multiply with 4, multiply this with 4. Okay, this will become 4x1 plus 8x2 equals to 160. Okay, and then minus, 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 this goes. So 5x2 is equal to 40 and x2 is equal to 8. And put this in any equation, this one, put in this one, x2 8, so x1 plus 16 is equal to 40 and x1 is equal to 24. So we have these 2 points, this point, 24 and 8, 2 coordinates, 24 and 8. Now work out the profit at each, find Z at each, at all of these, and the one which gives the maximum is our solution, or optimal, the maximum profit it gives. So find out Z. Z at 0, 0 is, of course, is 0. Okay, not difficult to find. Z at 30, 0. Just put it in the here. X to 0 and 30. 30 multiplied by 40 is 1200. This is 1200. And Z at 0, 20. 20 multiplied by 50 is 1000. And Z at for 24 and 8. Which means it is how much? 24 multiplied by 40 is 960. Okay. And 8 is 400. So this is 1360. And our solution is this one. Which means what? Make x1 is equal to 24 x2 is equal to 8, z is equal to, this is our solution. And in exam, I would like to see, when I am checking your exam paper, this box, so that I can, the person who has done right, I just give the right marks. Okay, who has done wrong, then I have to see it properly. Okay, this makes my life easy. If you make your life, of your instructor's life easy, he will make your life easy. Okay, if you make his life difficult, he will make your life difficult. All right. Now this is one method. This we call it corner point method. This is a corner point method. We have worked out the corner point method. Another method is called the isoprofit line method. Isoprofit line method. Now, isoprofit line method is that we equate it to some value z and find out and draw it. Draw the what we call it, straight line. Since this is also a straight line, okay, make z equal to, let's say, 800. Assume z is equal to 800 and solve this equation. Find out x1 and x2. 800 is equal to 40x1 plus 50x2. Then when x2 is equal to 0, x1 will be equal to 20, right? And when, which is x2 is equal to 0, and when x1 is equal to 0, x2 will be equal to 16. Yep. So what we do is, we select some number here such that we can draw this profit function within the feasible region. Okay? So this is our feasible region. And I will maybe use red color. Oh, these are the points, about 20, this is, let's say, this is 20 here, and this is about 16 here. Okay, this is 10 and this is about 16 here. We join these 2 points. Why it is called isoprofit? Iso means same. Any point over here, you take it, any point here will give the same profit. Any point, and there are infinite number of points here, right? Any number of points will give the same profit. That's why it's isoprofit line. Now the theory says, yeah.
How will you know the profit line? How will you find it?
Assume z some value such that it can be drawn within the feasible region. Okay? Once you have drawn it, this is the graphical technique. Once you have drawn it, then the theory says that the solution will lie on one of the extreme points. What you have to do is, you have to move to the extreme point. You have to move to the extreme point. When you are maximizing the profit, you will go away from the origin. When you are minimizing the cost, you will move towards the origin. Please listen. When you are maximizing the profit, you will move away from the origin. And when you are minimizing the cost, you will move towards the origin. So once you have drawn this line, you move away from the origin. right? And the extreme points, the last point hit in the feasible region is your solution point. Now, since this is a graphical technique, we should know how to draw parallel lines. And if you remember, when you were in grade 3, 4 or 5 or something like that, you asked your father that you want mathematical set. You know mathematical set?
Yes.
That mathematical set which has compass, divider, it has D, and it has two interesting things which you never know why they were for. They were triangles. Do you know why they were there? No? There were two triangles like this one, and one was a bit longer, 60 degree or something like that, 30 and 60 degree. These were called set squares. Okay, these set squares in the mathematical set, okay, the one which your father brought it for you when you were saying that you want it badly, and I think everybody had this desire to have that mathematical set. This is used for making parallel or perpendicular lines. You fix one and you move the other one on top of it. So if you fix, let's say, this one, you put this one on top of it, this will be like that. And you fix this one and you slide on the other one. And you make parallel line. You make one parallel line, you can make second, third, etc. Okay? That's what you do. You make parallel lines, alright, with this mathematical, set squares, and eventually when you make a parallel line, the last point that will be hit will be this extreme point. And this, since this is a graphical technique, you can read it from the graph, what are the coordinates, and that will be your maximum. Okay? So this is called isoprofit line method. Two methods, either solve the corner points or draw an isoprofit line and then parallel draw it, move it away from the origin until the last point hit in the feasible region is your answer. Clear? So we will now go through this very quickly.